It's my great pleasure and honor to introduce Professor Catherine Peters. She wouldn't need any introduction, quite known to all of you, but I just read a few lines about her. Also today, unfortunately, she twisted her ankle, so that's why she's sitting. But it's great that it was a minor incident. So Catherine is Professor of Geosciences and Geological Engineering, Chair of the Department of Civil and Environmental Engineering, and Director of the Undergraduate Geological Engineering Program at Princeton University. She is an expert in environmental chemistry and geochemistry, known for her leadership in sustainable energy technologies. She's a fellow of the Association of Environmental Engineering and Science Professors, and served as president of it in 2002. In 2020, she was awarded honorary board certification by Eminence in AAEES and received a Distinguished Alumnus Award of the CEE at Carnegie Mellon University. She's editor-in-chief of Environmental Engineering Science Journal. She earned her PhD in civil engineering from Carnegie Mellon University and her BSc in chemical engineering from the University of Michigan. She teaches courses in environmental chemistry, energy, and the environment, and sustainable design. Thanks a lot, Catherine, for graciously accepting our invitation to give this lecture. We are very much looking forward to your lecture. Thanks.
Thank you very much, and thank you to Hadi for inviting me to be a part of this summer school. It's such a pleasure. Thank you all. And when I fell out on the sidewalk this morning, I did not hit my head, so my head is in good shape, and I'm happy to give this lecture. Let's see if my slides can be viewed. So while the slides are coming up, as you all know, hydrogen is emerging as an important energy carrier for electric power production. And one of the things I want to remind us all is to think about hydrogen not as a fuel and not as an alternative to fuels, but as an alternative to mechanical and electrical methods of storage, because the hydrogen is produced from excess electric power production. So really we have to remind ourselves to think of it as a way of storing electrical power. And I have a little analysis in the talk today that will help us to think about that. What I'm going to do today is I have sort of three topics. One is I'll talk about salt caverns, but I'll talk about it in a way that's different from how we've talked about it so far. I'm also going to talk about cushion gas, which is something we haven't talked much about, but it's important in the context of any underground gas storage project. And lastly, I have some remarks about biogeochemical processes. We've heard from Nicole about the biological side of biogeochemical processes, and today I'll give you my perspective on the geochemistry side of those important processes. And also, I have a disaster story to tell you. A civil engineering professor, friend of mine, once told me that every civil engineering professor needs to have a disaster story to tell in their talk, so that I have one for you today that I don't think you've heard yet. Okay, so I start with this map, which we've seen already. I think Amartya showed it as well as others. So this is the United States. Underground gas storage has been operative for more than 100 years in the United States as well as around the world. And the by far the largest amount of this, the sort of 90% of this, is in depleted oil and gas reservoirs, with the remainder being in salt caverns or aquifers. And what text is on here helps to remind us of what I just said, which is that we're comparing underground hydrogen storage with other types of energy storage, like pumped hydropower and battery storage. And so it reminds us not to think about hydrogen gas as a fuel, but as an energy carrier. Okay, and this is another graphic that we've seen by now. So there is repetition in my talk, and that's a good thing for a school. This figure shows various underground places for storage of gases, and I will start by saying that I completely agree with the comments of Mark, who said we should forget aquifers for storage of hydrogen. I will combine that statement with some other things that we've heard. So yesterday, a speaker said, she reminded us that the underground is going to be a very busy place with lots of competition for good places to put gases. And then remember what Sarah Gazda said, which is that aquifers are pretty good places to put CO2 for one reason, which is that the capacity is calculated in an aquifer not just by volume of the pore space, but by solubility capacity, because the storage endpoint for CO2 in water can be as a solute, dissolved in the water, and that's not true for hydrogen and methane. And so aquifers are good places to put CO2, and if you remember what Sarah showed is that as the CO2 migrates vertically upward, there are convection processes because of the density differences, and that helps to mix the CO2 into the water as it goes. So my thinking is reserve those aquifers for CO2, and let's keep the other formations of the salt caverns and the depleted reservoirs for methane and H2. So now I want to say a little bit more about salt caverns. So I put on here that salt caverns range in size from 100,000 to 1,000,000 cubic meters, although the numbers for Spindletop seem to be different, but maybe even bigger than 1,000,000 cubic meters. Let me go on here. So I love this artist's graphic of a salt cavern, and I want to take a few minutes to a salt dome. I want to take a few minutes to talk about how did this salt dome formation get to where it is. So salt in a sedimentary basin would have been laying down hundreds of millions of years ago from the evaporation of an ancient sea. But salt, the halite rock, is far less dense than silicate rock. So as the sedimentary basin was forming over hundreds of millions of years, the very heavy silicate rock on top of the halite rock caused that halite to want to flow upwards. So through deformation and flow of this solid material, the salt came up out of buoyancy as it migrated vertically. And the result is this structure we call a salt dome, bringing the salt sometimes to the land surface. And I think of this as this gift the earth has given us, taking something that was very deep and bringing it to the earth's surface so we can use it purposefully for storing gases. I'm going to take a minute now to talk about the salt domes in the Gulf of Mexico area. So what's shown here in color is a relief map from satellite imagery of the salt domes that you can see from satellite imagery in the Gulf of Mexico. So I have some screenshots from Google Maps, so let me walk you through this. Okay, so we're going to look at the Gulf of Mexico area. So here is North America in image mode, and we're going to zoom into the Gulf of Mexico area. So my next image is zoomed into this area where we'll see Texas and Louisiana and a little bit of Mexico in the bottom left. So when we look at this image of the seabed of the Gulf of Mexico, yeah, I can do it with my, okay, what we're going to look at is this area right here. And what you see in the center of that area are salt domes, the tops of salt domes. And before I click and zoom into there, look at Houston, which is just above this, just north of here. The area of Houston is about the size of all this collection of salt domes. It's a very huge collection of salt domes. There it is. And so these are salt domes that have risen so far to the surface of the seabed that you can see them as features. And now we're going to look at, we're zooming out again, and now we're going to look at Louisiana. So you see New Orleans and Lafayette, and we're going to look just to the south of Lafayette, where there are some salt domes that have risen to the land surface in Louisiana, and they have formed features on the horizon there. So we're looking at this area right here in the red box. Okay, in this area we can see 4 salt domes that have altered the horizon, and the upper left one is called Jefferson Island. In Louisiana, they have named their salt domes islands. Even though they are not surrounded by water, they still call them islands. So that's Jefferson Island, and I'm going to come back to that one. And then Avery Island, which has its name here, is a famous place because how many of you know about Tabasco hot sauce? It's very popular in the United States. Okay, the Americans here know about Tabasco hot sauce, even some of the Europeans. So Avery Island is famous because that's where Tabasco hot sauce is made. And then there are 2 more of these salt domes in this image, and I put a measurement marker there about 3 1/3 kilometers. So I measured on Google Maps, 3.5 kilometers is about the size of the city of Delft from north to south. So these are big structures, and these are pretty much right at the land surface. Okay, now I'm going to go back to talk about Jefferson Island, and what you see, zooming in to look at Jefferson Island, which is the deep green colored area, is just to the southwest of it is Lake Peigneur. And this is where I'm going to tell you about a disaster story. So in the 1980s, the Diamond Crystal Company was mining salt from this salt dome. And not through solution mining, it was through physical mining. They had shafts and drifts, and they were bringing out solid salt. In November of 1980, Texaco got permission to set up an oil rig in Lake Peigneur. Oh, and I wanted to remind you, because this is relevant, I'm going to jump back. One of the reasons that salt domes have been such great interest to the oil and gas industry for more than 100 years is because when that salt dome migrated vertically over geological time, it bent the sedimentary layers in the basin and caused traps to form adjacent to the salt dome. And that's very nicely depicted in this graphic here showing the traps for gases shown in green here. And so there are lots of places around salt domes where oil and gas would have been trapped, and that's why they have been of interest to capture oil and gas for years. Anyway, so Texaco was interested in exactly that around the Jefferson Salt Dome, and they set up a rig right in the lake, and we're going to drill straight down. And so when they were drilling, it was November 20th, 1980, and something went wrong with their drilling, and the next thing that happened is that down in the mine where the workers were, water started to come in very quickly. And so the drill had gone through the bottom of the lake and into the salt mine, penetrating into the mine. And the workers had protocols for this, and they got out quickly. They all had to come out very quickly, and they followed their protocols, and they got out safely, and no one died. The workers on the rig figured out something was going horribly wrong, and they followed their procedures, and they got in their boats and skedaddled out of there, and no one died. But what happened was this hole in the bottom of the lake started to get bigger and bigger and became a huge whirlpool and took everything with it. The whole rig went down the hole, 11 barges went down the hole, a tugboat went down the hole, and 65 acres of surrounding landscape all went down the hole, and all the water from the lake went down the hole. It took 3 hours for this to happen, and then it was a dry lake, but just momentarily, because then it became a depression that was shallower than the sea water in the Gulf Coast, which very quickly then rushed upstream, backwards in the river, upstream, and filled up the lake. And that itself was such a violent hydrologic activity that it ended up scouring that river and scouring that lake bed so much that the lake is now 2 or 3 times larger than what it was, and it's no longer a freshwater lake. It's permanently a brackish lake now because it's essentially part of the sea. So that's a disaster story that you probably haven't heard. Thankfully, nobody died, but it is a story about salt domes, and it's a story about mining salt domes for salt, which there's a lot of that in the United States, meaning not using solution mining. All right, let us return to our...
Still have gasoline station nearby, I see.
Okay. Yep. Okay, so this is another map you've seen before over the last few days. And this table I screenshotted from a recent review paper that's just come out. There are 4 sites where hydrogen storage in salt caverns is happening, 3 in the United States and 1 in the UK. In the United States, Spindletop is the largest. It's also one of the oldest formations that, or oil and gas sites, has been developed in the United States, dating back 120 years. And here in Europe, I guess we are on top of salt right now, and you guys, this evening we'll get to, no, tomorrow we'll get to see some salt caverns. So in Europe, my understanding is that there is a lot of untapped potential and capacity for further development. And salt isn't everywhere, but we live in a global economy when it comes to energy and energy storage. And so there's an opportunity for energy storage in Northern Europe to serve the global needs. All right, now I want to go through this example calculation on storage efficiency. And this is motivated by this sentence that we see a lot, and we've heard even at this seminar, this summer school. And it's even a sentence on page 1 of the brochure that Hadi has. So hydrogen has the highest energy content of any common fuel by weight, about 3 times more than gasoline. I don't like this sentence, and I don't think it's that helpful for us. So let's go through it. And this gets to my comment about why are we comparing hydrogen to fuels? It really should be compared with other energy storage options. So let's go through a little storage efficiency calculation to really unpack this, as they say. Okay, so imagine we have a salt cavern. We'll pick a hypothetical case of a sort of middle-sized 500,000 cubic meter salt cavern, a moderate depth of 1 kilometer, so we're at about 100 bar and 40 degrees C. So what do we need to be able to figure out how much hydrogen would be there? We need an equation of state. You've heard about equations of states, especially the thermophysical properties. Professor yesterday was talking about equations of state. And so let's look at some equations of state. So the one on the right is for hydrogen. Focus on that for a moment. So what we've heard, and what I'm repeating, is that the critical point for hydrogen is very low. And so the critical point, which is that orange diamond, is at very, very cold conditions. Below that, the gas would be, or the fluid would be 2 phases, liquid and gas in equilibrium with each other. But above that, it's a single phase, it's a supercritical fluid. But it's not very dense. And so the conditions that I'm looking at, the 40 degrees C and 100 bar, hydrogen gas would have a density of 8 kilogram per meter. Now, just for kicks, let's compare it to the other things that we put underground. So on the left, I have equation of state data for CO2 and for methane in one plot. And just so we're on the same page, what is a PVT? What is an equation of state? It's a PVT relationship. And I tell students that really I like to think of it as a P density T relationship. So what is the density as a function of pressure and temperature? That's the way I think of what is an equation of state. Okay, so on the left, we have density as a function of pressure for a single temperature, 40 degrees C. And on the left is a complicated set of curves because this came from one of Kurt Oldenburg's papers where he's interested in mixtures of CO2 and methane, so ignore that for now. We're just interested in the two end member curves, which are for pure hydrogen and pure methane. And I think that my arrows got moved around, but that's okay, because I have the numbers on the next slide. Okay, so we go and figure out from the equation of state for CO2 and methane, just for comparison's sake. Okay, and so we add them to our slide. So we've got the 8 kilogram per cubic meter for hydrogen, and in the same pressure temperature condition, methane would be 10 times more dense than that by weight, and CO2 would be almost another 10 times more dense than that. Well, you're thinking, well, carbon is the difference. That big carbon atom, that's heavy. Hydrogen, those are two little tiny atoms. Carbon is a big giant atom compared to hydrogen. That must be the difference. So let's get rid of that difference and see if that explains these numbers. So in the next column, I say, well, how about just molecule per molecule? So let's look at mole density. And so when we account for mole density, then methane and hydrogen look about the same, 4,000 compared to 5,000 moles per cubic meter. But still, CO2 is much more dense. And why is that? Why is that? Molecular interactions. You know, when we teach students about physical chemical properties of fluids, we start by teaching the ideal gas law where there's no molecular interactions. Those molecules don't even know that there are other molecules around. But under high pressure, those molecules see each other and they feel each other. And CO2 is fundamentally different from hydrogen and methane in the sense that it's got those oxygen atoms, and those oxygen atoms are so electronegative that they pull electrons toward them, and they create internal dipoles. And that internal dipole creates what's depicted here by those little bond dipole arrows. And the separation in color, pink and blue, meaning that that molecule has some ability to attract to other molecules like itself. You can think about this like the hydrogen bonding process in water, which is far stronger, but it's the same thing. That's why water molecules are attracted to each other because of internal dipoles, and same thing for CO2 molecules. That's how they're attracted to each other, and that's why you get this very special property that CO2 can be quite dense. Now we're going to go on to talk about energetics, so we'll forget about CO2 for the moment, but we'll come back to it when we're talking about cushion gas. So now I have here the heating value, which is a measure of how much energy is in the bonds in the molecules. And here, this is the basis for the sentence in red, that hydrogen has the highest energy content of any common fuel by weight. And I put crude oil there to show you what that factor of 3 is the basis for. But if we think about energy density, meaning energy per unit volume, that's our practical term, hydrogen falls to the bottom of the list. And this is my message about, so let's not talk about hydrogen as a fuel, because in terms of underground gas storage, methane wins this game. So let's not compare it with other fuels. And then the last thing so then I just took this volume capacity of 500,000 cubic meters and said, well, it's how much energy is that? This is how many terajoules it is. And then I said, well, how much could be done with 500 to 2,000 terajoules? And then I went and found the electric power consumption per day for some major cities as well as for the entire of the Netherlands. So with our hydrogen gas in this hypothetical salt cavern, we could power London for a day or a little more than a day. And with methane, we could power New York City for a few days and the Netherlands for about 6 hours, it looks like. So just to give you a sense of how much energy we're talking about in these formations. Okay. Now my second topic is about cushion gas, and this is my introduction slide to this topic. And for those students who are online, you might want to screenshot this because these are two very good papers that I think are helpful. The one on the left is a little bit old now, but it's a great paper by Kurt Oldenburg at Lawrence Berkeley National Lab, where he was looking at the geophysical processes of choosing CO2 as a cushion gas for methane storage, as opposed to just having methane be its own cushion. And on the right is a quite recent paper by Lauren Beckingham, who's at Auburn University, who's working on compressed energy storage, including hydrogen. And she did this paper where they used reactive transport modeling to look at the water-rock interactions and the geochemical reactions that might occur when hydrogen or when CO2 is used as a cushion gas. So let me say more about the physical processes. One of the things I like about Kurt Oldenburg's paper is that he included a PT phase diagram. A PT phase diagram shows us where the critical point is for a gas as well as the phase boundary between liquid and vapor. And the reason he included this is because he wanted to draw attention to the fact that coincidentally, the pressure temperature profile, a typical pressure temperature profile through the subsurface would go right through the critical point. And that makes CO2 unique, and it's just coincidence. And it is very important for us to keep in mind when we're thinking about the equation of state, the density variation of CO2 with depth. And so somebody yesterday, might have been Tony, I forget now, somebody had made an equation or a PT phase diagram and put methane, CO2, and hydrogen all on one. Was that you, Tony? No, okay. Reiner did that. That's right. Okay. Yeah. And so CO2 is the only one that has this property of, so that's what that gray band is. And why is it curved? It's curved because it's a log scale on the y-axis. So with a linear change of hydrostatic pressure with depth and linear change in temperature with depth, and you end up with this PT path. So now we're thinking about cushion gas. So what is it that makes a good cushion gas? A good cushion gas is something that you can press on and it will compress and not push back too much. So that's compressibility. And so I put here the way that thermodynamicists think about compressibility using this factor Z, this compressibility factor. So here you see it as a way of modifying the PVT gas law. Does methane have this amount of compressibility? Does hydrogen? Well, let's look at this a little bit. Okay, so this is my addition now. I've added two different PT profiles, one for a colder aquifer, let's say an aquifer that's maybe higher on the earth, and a warmer aquifer that has a warmer land temperature. And so what I want you to think about, especially those students who are online, is how, for CO2, how does the density change with depth? And so what I want you to do is open your notebooks and sketch how density changes. I'm not going to do it with my hand because I don't want to tell you how it happens. How density changes with depth. And depth is, so I've flipped the axis now. Now I'm showing depth as 0 at the top and increasing going down. And so that's like taking that PT diagram and just flipping it upside down. And I will remind you that we've seen this. I've spotted at least 2 speakers who included this exact profile in their talk. Sarah Gazda was one, although it was on the slide where she started to wrap up and say, I don't have time for this, but you did see it. And so I want you to see if you can do that. And then if you have time, also do curves 1 and 3 for the colder aquifer and the warmer aquifer. The colder aquifer doesn't go through the critical point. It goes across the gas-liquid phase boundary. So what does that mean in terms of compressibility? And then for the warmer aquifer, which stays in the, or has a continuous transition from gas into the supercritical region. And so hopefully you've done it, students. Now let me tell you what the answer is. Okay, so this is a graphic that I grabbed that shows this very nicely. So here's how density changes with depth. And this is this very coincidental thing that the critical point, pretty much we're going through that point. And that is a point where there is this transition from low density to high density over a very short delta P. And that's what makes CO2 a good cushion gas mechanically. And so that was the point of Kurt Oldenburg's paper, is that CO2 has this very special property. Lauren Beckingham, who I mentioned, has also looked at CO2 as a cushion gas, but focused on the geochemical reactions. She looked at how those reactions might alter porosity in the formation. And I just screenshotted one of her results graphics where she's showing the porosity going from 25 up to 32%. So that's a significant change, especially, for example, in a carbonate formation where the introduction of CO2 forms carbonic acid, which drives acid-driven reactions like the dissolution of carbonates. So you notice I also put in here a most recent tweet. This tweet is from just a few days ago. So for all the students out there who are interested in postdoc opportunities, Lauren just got a DOE Early Career Award to study hydrogen gas storage underground at Auburn University. So if you're interested, then by all means reach out to her. That's all I'm going to say about cushion gas. And now I want to move on to talk about biogeochemical processes. We heard where is Nicole? We heard Nicole talk about these processes from a biological perspective, the microbial perspective, and then my remarks today are going to add the geo part of that biogeochemical process. And what Nicole said is that hydrogen is a universal donor. So I wrote it's an electron donor, but emphasizing it's a universal donor. And it reminds me of like hydrogen to bugs in the underground is like O-neg blood at a hospital. You know, it's the universal donor. And so what I have on my slide here is something that you saw a little similar to what Nicole presented. So Nicole presented the redox sequence, and I have a similar redox sequence. So the question is, if hydrogen is electron donor, what can it give its electrons to, and what do the microorganisms want it to give its electrons to? And so I have a simplified version of what Nicole presented, showing only oxygen, iron, sulfate, and CO2. I put oxygen there as a reference. If it's at the top of the list. It's the most thermodynamically favorable as an electron acceptor. And if oxygen is present, then that's who's going to get the electrons, no question about it. But as Nicole said, there was nitrate on the list, manganese. I left those out, but there's an order here. And so the ones I kept in are iron, sulfate, and CO2, because iron, sulfur, and CO2 are definitely what we need to talk about as having a presence in these subsurface formations. So I just got done talking about CO2 as a cushion gas, and Kurt Oldenburg studied the mechanical processes of compressibility of CO2, and Lauren Beckingham studied the geochemical reactions creating porosity. There's another big paper to write, which is CO2 as a cushion gas and its role in this process, which now we've heard about quite a bit. People have used the terms in the last couple of days of biomethanation. This is a methanogenesis process, meaning the organisms that would be responsible for this are capable of generating methane. And I'm reminding again that there were the bacteria, and there were the archaea, and the archaea would use CO2, and the bacteria would use acetate. But the result is the production of methane. And when I started looking at this, I found this fascinating, because I started out this talk saying, let's not talk about H2 as a fuel, let's think about it as an energy carrier and energy storage for electric power production. But this is where that interface becomes blurred, because now we have either the challenge or the opportunity of producing methane. And so what I want to say here is that I want to underscore what Nicole said, which is that this reaction is going to happen. These organisms are going to be there. And there was some conversation about how can we stop this if we don't want it to happen. And I think that, to me, when we had the list of things on the board, I think that's the biggest scientific question, is understanding this process of methanogenesis, if CO2 is going to be there. And if we use it as a cushion gas, which it seems we should, then it's going to be there. And so then this is something worth studying, in my opinion. Oh, I have one more slide on this, and as we've heard, this is being called power to gas, and what I've shown here on the right is not only acetate and CO2, but also methanol is the third way that's identified that methane could be produced biologically. All right, I want to say a bit about H2S. That's a quite separable topic. It's also a biologically driven process, but it's different and separable, and we should talk about it separately. This is the one that's definitely a problem. There's no potential benefit to this one. There are all sorts of reasons why we should be concerned about H2S, and Nicole reminded us of just how toxic it is at very low concentrations. Even if it doesn't lead to human exposure, it leads to economic damage in terms of gas souring. There's the potential of precipitation with iron, and if this happens, it can produce biomass that would plug up the pore space, et cetera. So there are all sorts of reasons why this would be problematic. However, it's really important. And if you learn one thing from me today, it's this. This reaction is relevant only for the oxidized form of sulfur. Okay? So it's a sulfate reduction reaction, meaning sulfate is being, through a redox reaction, electrochemically being reduced to sulfide, and that's in the H2S. Where is sulfate? Do we have sulfate? Is it ubiquitous underground? And the answer is no, it's not. And so what are the minerals that contain sulfates? So I put anhydrite and gypsum. The calcium sulfates, where are they underground? Well, they are in the salt, in the halite rock. Why? Because sulfate, the oxidized form of sulfur, is very ubiquitous in marine waters, in the seawater, and it was also present 100 million years ago when that salt formation found. So in evaporite rocks formations that form halite, that also precipitated the sulfate at that time. So calcium sulfate is a pretty abundant component of these salt dome, these salt formations in the halite rock. It's there. When salt mining is done with say, fresh water, it dissolves to a much lesser extent than the sodium, potassium chloride, and so it tends to build up in the solid, but it's still there. So in salt caverns, yes, I think we do need to worry about this because sulfate, the oxidized form of sulfur, is there. Let's now talk about depleted oil and gas reservoirs. Depleted oil and gas reservoirs are what we call reduced environments. Reduced, meaning chemically reduced. The iron exists as ferrous iron, not the oxidized form of iron. The sulfur exists in the reduced form, not as sulfate. So the minerals, and I should have put them on my slide, the minerals that contain iron and sulfur that are part of sedimentary rock, that come from igneous rock, they are sulfides. So pyrite, pyrrhotite, these are iron sulfides, okay? And so it's really important for us to know that even though iron is abundant and sulfur is abundant, oxidized sulfur is not abundant in depleted oil and gas reservoirs. Now, there are some caveats to that. Sometimes in the oil and gas industry, seawater is introduced for various purposes. I just said seawater contains the oxidized form of sulfur. If seawater is introduced into oil and gas reservoir, that could bring in sulfate. But that's generally a bad idea, and the oil and gas industry avoids it because when sulfate is introduced as an anion in the water, it readily precipitates with whatever divalent cations are there. And the one that's there that everyone knows about is barium. Barium sulfate precipitates as barite, and that is so insoluble, and it's a problem in the oil and gas industry because it leads to formation damaging, meaning it cements up the formation. So that's something that's generally avoided, but it is one way if we're thinking about trying to keep sulfur, the oxidized form of sulfur, out of a formation is to not introduce seawater. So anyway, that's my main message, is to be very clear about the redox state of the formation. And in my thinking, I don't think it's going to be a big problem putting hydrogen gas into depleted oil and gas reservoirs because the sulfur is not oxidized. So this reaction on the right hand, for the most part, isn't going to happen. That's my prediction. And that is my last slide. And thank you very much for your attention, and I hope to take some questions.
Sure. Thank you very much, Catherine. Questions, Bart?
Thanks a lot, nice presentation. Just like to echo on or comment on what you said for the salt caverns. I've seen quite a bit of formation waters, produced waters, compositions. Also, even in reservoirs, they do contain often low levels of sulfate still. But I was amazed, and I think with me, Remco as well, about the levels of sulfate we found in these salt caverns. It's
Yes.
is tremendously high. I've never seen such high levels of sulfate in any subsurface water samples that I've seen. So,
And it's in the rock itself, it's in the salt itself.
yeah, no, but of course, if you start putting in a brine and you have a sump, it will end up in the sump, right? So
Yeah, so I think H2S gas formation
Yeah.
should be considered a risk for salt caverns.
agree fully, yeah.
Yeah.
Thanks a lot. Cheers.
Thank you. Then Karin, then Jan.
Thank you for the interesting talk. I have a question about, because sometimes people are saying we can inject seawater into salt caverns, which would be helpful if you're building salt caverns out at sea, of course. It's close by. This will worsen this problem, right?
It will worsen the problem. The problem is already there. I think it's such a huge problem already. I don't know if you're altering it.
Okay.
It's because the calcium sulfate is already in the halite. It'll come out, yeah.
Okay.
Yes, sure. Can come to Jan and then.
Jan Garo from Geostocks, and I'm a bit curious about cushion gas and the use of CO2. Aren't you creating a problem with CO2 that you will not have with hydrogen or methane, for that matter?
Yeah, so which problem are you talking about?
Well, I mean, you could develop bacteria
Yes,
and so
right.
on.
And that's actually one of the things I hope we discuss in our remaining time, because to me that's a very interesting, is it a problem or is it an opportunity or a challenge? And it depends on your purpose, and I think it remains to be seen what is economically the best is to actually make the methane or to inhibit it. And it's a shame because CO2 is mechanically, and you know, from a thermophysical point of view, is the best in terms of compressibility. And methane doesn't have that ability. In H2, if we let H2 be its own cushion gas, it really doesn't have that compressibility. So we gain and we lose.
Thank you, Catherine. I've got a question regarding brine within porous media. You said that basically if we go to sedimentary basins, we don't have those oxidized sulfate.
Yeah.
But we do have brine, and that formation water could potentially, I suppose, depends where it originated when it went to, you know, migrate and fill the pores. So do you think that one of the site screening or site selection criteria could be to look at the pore water and to investigate what basically is causing the saltiness of that water, whether it's only NaCl or maybe some of those sulfates?
Well, the native brine in the reservoir is also reduced, meaning chemically reduced. It's also doesn't contain much, if any, sulfate. It's in equilibrium to some extent with the rock. But if new brine is introduced from elsewhere, particularly if water is being used from a seawater source, then we have the problem of we've introduced oxidized sulfur, and now we have the risk of H2S production, I think. What? Yes, yes.
So I think that follows up on your question. So if you have a depleted reservoir and the seal is salt, would
A
you...
depleted reservoir and the seal is salt.
Yes, would you expect any sulfate then, or is it
Yes.
also in the reduction state?
Uh-huh. Yes, wherever there is a halite rock. Yeah, if it's a halite rock, a salt formation, then there's going to be sulfate in it. Yeah,
Okay,
yeah.
so that should also be a selection
That's
criteria.
that's true. Yeah,
Okay, thank you.
yeah.
Hi, Guillermo Shagami from UPN. Thank you for your clarifying presentation. I really enjoyed it. And my question is about cushion gas. I have been running numerical simulations using carbon dioxide for injection in aquifers and methane for depleted oil and gas fields. I would like to ask you if I should consider another cushion gas like nitrogen or even hydrogen. I had seen a lot of literature about it, that they take advantage of this cycle of injection production of hydrogen, and they can use it also as a cushion gas.
Yes, it's just, there's a loss of, not loss, there just isn't so much efficiency that you get because it's not very dense and not so compressible. Yeah.
We have about 15 minutes, and it would lead naturally to, already has happened, the discussion around this subject.
Is this part of our session?
No, it's now I'm just going to shift it to your session, which is now discussion, so that I want to motivate everybody to ask questions like this, and then you can have engaging.
Okay, Nicole and I have
join you
a
as well,
plan.
and I can give you a hand for microphone.
To kick off the transition from my talk to our discussion section, I have a bit of a game to lighten things up. This is a quiz to see if you've been paying attention. This is the quiz. This is the Who Said That quiz. Okay. There's one person, one speaker, who used the word land hog. Who was it? Does the person who said the word remember it was them? There it is. It's Tony. Very good. I
said it on purpose.
Yep. Who said, don't say antibiotic? Who swore and had to have their video bleeped before Reiner? Yeah. Who said, not a revival, a vival? Yeah, you remember, it's Eric Verschuer. Yeah. Who said, get some fresh air? You all were paying great attention.
Thanks a lot,
Okay, and just before we now continue to discuss here in the plenum, I want to again encourage people online to go on menti.com. We did that yesterday, so you should all know how it works. So punch in the code you see on the screen, and then just, like, we want to know, so now we heard a lot of scientific topics, but then do you think you're still missing something? It's also good to know for us. So what do you want to learn more about? What is something you say, this is missing, maybe not only from a research perspective, but from a training, learning perspective? So we just want to see something. It will pop out on the screen now over time. But then in the meantime, we can discuss a little bit further. And yeah, we were already discussing. So what I want to emphasize a little bit, maybe some comments on that. So we had talks which were quite scientific, like based on scientific field, like microbiology talk, geochemistry talk, thermodynamic talk. So, but then again, we see that all the scientific fields are needed. We need the interdisciplinarity to really bring this forward if we want to achieve high TRL in a few years to come, which is a challenge. So how do you see this aspect? Where do you think is the way we should work together across the fields? Where are the main topics? So somebody has a comment, so please go ahead.
Can you scroll so it, I think it gets, they're added to the bottom and we're.
I don't know if I can scroll.
Let me see what I can do.
But please, come on.
Yeah.
Or if
Yeah, some are texted here. We can take the list later, but if you want to just say it in person, please.
Actually, it is not the thing that we didn't discuss so far, but I would like also again emphasize that we still need to share our knowledge or our experience from natural gas storage clearly and just share it together, because I think we have good experience over the board that about the natural gas storage. Everybody, I think, is interested to learn more about it. I think it can also trigger and also initiate for hydrogen storage as well.
Okay. Who is? Oh, yeah. It's on.
Yeah, Geon Strobel, Iolipa Energy Storage. The interdisciplinary thing is, for me, when I started my research, is because I'm a weather engineer and I had no idea about microbiology. So I had to start from the beginning about growth curve and everything. So for me, it's when you talk about weather engineering, you talk a lot about mixing and modeling, but you have to talk also a lot with the microbiology just to like understand how this one works actually on really small scales. And for me, this is one of the biggest interdisciplinary thing you have to do.
Tony, I come in a second.
Sure. So yeah, I think, you know, the perspective of thinking about hydrogen as a storage mechanism is the right way to think about it. And if that's the case, we really need to think about like round trip efficiency. So like electricity to hydrogen or gas to hydrogen storage back and then to use, right? Because you know, that number is not going to be one. You know, and for instance, if you add a cushion gas that's not the native gas, then there's going to be a separation on the surface that you would need to incorporate. And I think just running through some of those cycles would sort of help people to understand where the real research opportunities are.
Let me respond to that. One of the things, like, Hadi, if you do this again, you know, I think that a missing community here are the energy storage people, not the hydrogen people, but the people who think about batteries and hydropower and putting hydrogen in the context with that.
We have some colleagues
Yeah.
Yeah. I want to echo that because I don't know who said it yesterday, but we are all, let's say, technical people mostly here. And we all have our disciplines and interests, but what is indeed lacking also is a little bit the demand part. And this morning I actually had to laugh because so there was this comment like, let's really work on the infrastructure also, right, for hydrogen, etc. This morning I parked my car, and obviously it definitely will have a reason. But before the parking lot, this 3-4 staged parking place was a big sign: electrical cars and hydrogen-fueled cars forbidden. So there's definitely work in that area as well.
Excellent. So techno-economics, also value chain, and all the energy system.
Yeah. Because they also need to hear from us.
Absolutely.
Yeah, they need to hear the challenges.
These are our own students, I guess. They knew that our guests are here. So, Serge.
Yeah, thank you. I think I agree with also Nicole that we have heard a lot of science and things that are going on in the laboratories and the computer models. But I think, the validation with the real experience in the fields, that will be a major challenge. And I think, hopefully in 5 years' time or something, we'll have here operators on the floor who are presenting proudly their work. And they can, let's say, they can raise the new questions to us. We have these issues to be tackled for safety, etc.
In fact, what Serge mentioned, we spoke with one of those operators, and we asked them, what data are you collecting so that we consider them in our research? They were coming back to us and said, you should tell us what should we monitor or collect as well. So it's a kind of two-way street of questions. More questions?
I would just like to second the comment which surfaced up as the very first When you, Nicole, said the question, so very first one was business case, and when I present my work, there is always question that people ask me, what's the rate of, I don't know, like we've got per wind or per gas and other renewable energy, you've got such amount of pounds per megawatt. And somebody always asks me, what's about hydrogen in terms of storage, what it would cost us, and I'm never able to answer the question because I don't know who knows that. So in terms of underground storage and business case for hydrogen storage, I would maybe add this aspect.
Just on that, us geologists and reservoir engineers, we're used to being upstream and thinking with an upstream mindset. We're the heroes, you know, we're the people that produce the supply. When it comes to storage, we're no longer those heroes. We're not upstream, we're midstream, and we need to take on that midstream thinking. So we're going to consume from the upstream, which is going to come from, you know, electrolyzer stacks, or if we're talking about blue, from oil and gas that other geologists have found. And we're going to pass that down to meet the demand side on the downstream. But we actually have a totally different position in the value chain now. And I think that takes a different mindset where we need to be talking to those that will be the new upstream, if you like.
The new upstream.
Bring
Yeah.
next time.
Yep.
Well, my name is Simon. I'm actually working for a green hydrogen developer. So we're working for Hynamics. We are developing projects for green hydrogen. And first of all, I would like to congratulate on this great audience which you put together. So it's really brilliant to see what disciplines are involved here. We have universities, we have Geostock, so we have lots of companies, and it's been a very pleasure for me to understand what the challenges are in developing underground hydrogen storage. A comment on the industry involvement. So we definitely need to have exchange between the green hydrogen developer, because those will be the customers that need storage of hydrogen. The challenge there is that for the small projects we are currently working on, we are still struggling to get all the regulations in place. We are still struggling with our business cases, but there will be a huge demand from the industry in the next coming years for underground hydrogen storage at large scale. So all the challenges we have talked about in the last 2 or 3 days, we need answer for those quick. So I'm really pleased to see that all of you are working on that. And I'm looking forward to the next, hopefully, next summer school, maybe here, somewhere else, and fully agree that we need to have this collaboration between the hydrogen industry and underground storage. Because in order to make the connection between the hydrogen production and having hydrogen introduced in industry processes, which are used to being at base load, we need some kind of storage. Otherwise, we are not going to get the hydrogen introduced in industry projects.
Yeah, so one thing I was reflecting on once again, based on one of the pictures you've shown with the different storage caverns, the different production caverns, the aquifers, reservoirs very close to each other, is how do all these underground activities influence each other? I think there is no question that we can engineer our way out of many of the problems that we have discussed today. Whether that affects the business case in the end is something that needs to come, but what I'm missing a little bit is interaction between gas production, compressed energy storage cavern right next to a water, or to a brine production cavern right next to a natural gas production cavern. Not only mechanical interactions, but maybe even chemical interactions. We all know that the underground is not as tight as we sometimes think. Different aquifers being in contact with each other's and reservoirs. So that's one of the things I would like to see a little bit more attention to.
Yeah.
Yeah, I just want to comment because I think it's a really good point. Because we very often paint this picture of this will be the hydrogen economy of the future. Everything runs on hydrogen, perfect. And this is where we are now. But then again, how do we come to this? The transition, we will not switch off natural gas pipelines off, hydrogen in. This is not going to happen. So how will actually with this stepwise process where we have both simultaneously, probably for quite a long time, how this actually will work out. So I totally agree that we need to also think about the in-between where we don't have like 100% hydrogen, 0% hydrogen. So, yeah.
Yeah, and maybe a related thing to that, the Netherlands is quite full already with activities, both above ground and underground, and also offshore. We saw a TNO study being presented about the feasibility of TNO EBN, I should say. I saw Silk frown a little bit there. But even the offshore is already quite full. So how do we fit this in, not even with underground activities, but in general with activities in general?
Students. Milemai.
Yeah, so what I think is a very important one as well, it has been named a few times, but it's the public perceptance. I think we all considered it as one of the main things that will be a problem in the future. And I would be very interested to learn how we can engage them, how we can make them happy. It might not be our jobs in the future, but I think it's important for all of us to know how it will work.
I tried to bring Mayor of Delft to this workshop, but maybe next time.
I was thinking, let's say if we go into hydrogen economy in coming 5 or 10 years, what about the requirement of materials to make sure it happens? Like, number of wind farms or solar panels, and also in the source level, like number of electrolyzers. And if we think of this as a startup economy, then what about human rights violation in making sure these are extracted to support the society? How does that affect?
Susan, you look like you want to say something, no? Just, I have a feeling.
We did a lot of workout this week.
Okay, I introduce myself again. I'm Guillermo from UPM. I totally agree with what you were saying about, I guess we have to be humble about it. And when I listen to words like decarbonization, that we are gonna change from one day to another to using hydrogen or renewable energies and forget about fossil fuels, I feel it's too much. I guess a transition to renewable energy should be considered a victory. To reduce the use of fossil fuels should be considered a victory. And coming back to this question, have been reading more than 60 papers for the last month, and I don't think you miss any topic, to be honest.
Can you repeat that? I didn't hear what your last comment was.
What? I didn't think you miss any topic in this school. It was.
It's okay. Yes.
Oh, hi. My name is Herminio from TU Delft. I wonder how is it going to be 5 or 10 years from now when we have the energy matrix based on hydrogen, if it is going to be able to provide the same amount of energy that we spend today in the entire world, and if the price is going to be affordable or if it's going to be much more expensive than now.
Oh, yes.
Yeah, so we're here together with a bit of a subsurface focused community. I'm just putting it bluntly. But of course there's also a surface element to hydrogen storage, underground hydrogen storage. So wells and facilities. And I miss a bit the relationship between the subsurface and the surface. So what happens in the subsurface and how does this affect what is required in terms of equipment, wells at the surface. So I think it would be good to have a bit more focus on that in the next summer school, without making it too broad, because also we should be wary to not expand too much beyond underground hydrogen storage, I think.
So Remco, your point is we keep it geoscience, but also relevant as well to the geoscience. So the core stays geosciences. Good. There are plenty. You can take a note of this, right? It just your account is professional enough that extracts, or you need to pay for it?
I think I can download the results.
Okay. Some features come at cost sometimes.
Yeah.
Any other comment, especially those who have not contributed so far? Today we are going to be a bit more asking you, please say something, or what would you think most? I'm trying to see. Did you enjoy the workshop so far? Yes.
Let me make one more comment. You had a session on the first day that was a panel that Sam led about what can we learn from the CO2, and I think that was a great idea and inspired because not because CO2 is at all like hydrogen. And someone made the comment, why are we even talking about CO2? It's not even a fuel. But the research, the research infrastructure and the way researchers turned toward that problem over the last couple decades, and the way in the United States, for example, the way the Department of Energy turned its ships towards this problem and set up these demonstration sites in regions, as Mark had a map in his talk, and Sarah talked about the success of the demonstration projects. One of the things I was involved in is the National Risk Assessment Program that the DOE set up to figure out how we're going to monitor these sites. And so I think that there is so much we can learn from what I'll call the research infrastructure of how the scientific and engineering community turned its sights to address this problem. And that's what we need for hydrogen. And as far as I know, that never happened for storing natural gas underground, because it's been going on for 100 years, and there was never a mature research, scholarly research community to work on it suddenly. It just was done. Yeah.
So 1 minute, maybe you can summarize, then we go to lunch break.
Yeah, so I think we heard a lot of very good comments. I also agree. I mean, there are a lot of topics for the hydrogen value chain. You can start from production to end use, acceptance, business cases. I think having something specifically for the underground is very good, because we already see how complex already this topic is. But of course, there's a lot of other research going on. I've seen several publications now on public acceptance of hydrogen. So just keep an eye on these specific papers. And so there are people working in the social science. It is not overlooked. They are doing things on that, probably also for the other topics. But yeah, then I still want to encourage everyone, let's work together, make this interdisciplinary, because that's important, not just with our typical research eyes on our field and say, the microbes are the coolest. Of course they are, I'm a microbiologist. But keep everything broad, work together, not do modeling with any experimental data. That doesn't make sense. Don't do just experimental data and then don't tell the modeler. That also doesn't make sense. So keep in touch, thanks. Work together. I think that is super important, and I think these events really help. So thank you, Hadi, for organizing. And I think...
Thanks a lot. So we go to, let's thank Catherine and Nicole once more.